Yeah, so we have the notes for section 10.5. Adjust the camera here a little bit. There we go. Which is testing convergence at endpoints. So first thing we've got is the integral test. So let an be a sequence of positive terms. Suppose that an equals f of n, so where f is a continuous positive increasing function for all x of x for all x greater than or equal to n. So at some point, this function goes positive, stays positive. Then the series and the integral either both converge or both diverge. So does this converge? So as long as n is greater than 1, we get a positive decreasing continuous function. So I can try this instead. So 1 over x root x dx. So this is the same thing as 1 over x to the 3/2 dx, which is the same thing as x to the negative 3/2 dx. Okay. So let's see here. What do we got? So do the antiderivative, we would need to add 1 to the exponent, so that makes it -1/2. And then the reciprocal of that goes out front, -2, and we're going to evaluate from 1 to infinity. So keep in mind that this is the same thing. -1/2 is a root on the bottom. So -2 over root infinity minus -2 over root 1. So this is 0 plus 2. So this is 2. So since my integral converges, I get a number. The sequence also has to converge. So that's the integral test. Okay, harmonic series and p-series. So the integral test can be used to settle the question of convergence for any series of this form, where p is a real constant. Such a series called the p-series. P-series with p1 is the harmonic series. So approximately how many terms of the harmonic series are required to form a partial sum larger than 20? Okay. So let's see here. How do we want to think about this? Okay. So if we look at this, let's look at the graph. So if this is, we're graphing 1 over x, because if p is 1, this just becomes 1 over x. So it looks something like this, and we got this, and then we've got, so this point here is at 1, 1. So this has an area of 1. And as this tails off, we get, if we keep going out, we get half, third, fourth, so on and so forth. So 1 plus, there you have that's 1/2, these are all 1 unit wide, plus 1/3, plus 1/4, so on and so forth. So this stuff down here ends up just being the natural log of 4. So I know that 1 plus ln of n has to be greater than the harmonic series, which has to be more than 20. So this kind of stuff doesn't matter. So we want sum larger than 20, so larger than 20. So the natural log equals 19. Subtract the 1 across. To get rid of the ln, everybody becomes an exponent on an e. So e to the 19th. So let's see here. What is e to the 19th? Doop-a-doo. Probably a very, very large number. 178482301. So you need at least that many terms before the sum goes more than 20. Because notice you're adding smaller and smaller values. The next would be a 5th, a 6th, a 7th, and 8th. So it's going to take a lot of terms because eventually you're adding very, very, very small values. Okay, limit comparison test here. So suppose that a of n is always more than 0 and b of n is always 0 for all n greater than some number. If the limit of a of n over b of n is equal to c, and c is some number between 0 and infinity, then they either both converge or both diverge. If you get 0, and b of n converges, then a of n also converges. If you get infinity and b of n diverges, then a of n converges. So the thing to be careful of is here is when you choose your b of n or your a of n, you need to know whether it is a convergent or divergent series. So let's look at this guy. So determine whether the series converge or diverge. So we got this. Okay. So typically what you do is you just say for n, when n gets very, very big, what does this function look like? So for n large, this essentially becomes 2n over n squared, because these plus ones don't matter, which just would reduce to 2 over n. So doing the limit comparison test, we are going to take, so this is our an, and this is our bn. So so a of n over b of n so this gives us, no, sorry, forgot the limit. So 2n plus 1 over n plus 1 squared times n over 2. So flip it and multiply. Okay. So this becomes limit as n approaches infinity of 2n squared plus n over 2 times n plus 1 squared. So this would become infinity over infinity, so we have to do L'Hopital's. So this becomes 4n plus 1 over 4n plus 1, which is so we get 4n plus 1 over 4n plus 4, which reduces to just 1, because only the lead terms matter. So since this is a number between 0 and infinity, they both have to do the same thing. 1 over n is the harmonic series, it diverges. So since 1 over n diverges, and I got a number, this guy also must diverge. Okay, so let's look at this one. So 1 over 2n minus 1. Let's see what we get. Okay. So for n very, very large, this function behaves like that function. So we compare the given series. So original function, reciprocal of the other, like this. So this would just actually become, oops, put that minus 1 in the wrong place, minus 1. So the limit as n approaches infinity of 2 to the nth over 2 to the nth minus 1. Okay, so let's see here. So we've got this 2 to the nth, so we're going to do a trick we did in the previous section. We're going to divide everybody by 2 to the nth, because that gives us 1 over 1 minus 1 over 2 to the nth, which, if you do this, just gets out to be 1. So this is a geometric series, It converges. Your r value is 1/2, which is less than or equal to 1. So since b of n converges, and you got a number for the limit, the original function also converges. Okay, so for n large, this thing is essentially 3n over n cubed, which is 3 over n squared. So the p-series test, this guy we know that this one will converge because p is more than 1. So let's see here. So do our comparison test. So original, reciprocal of the new, because we're dividing by a fraction, so I might as well just flip it and multiply. So this becomes the limit as n approaches infinity of 3n cubed minus 2n plus 2n squared over 3n cubed minus 6n. So this would give me, let's see here. Only the lead terms matter, which comes out to be 1. So since that's a number, this converges, which means the original one also converges. So if you remember, if you get a number for the limit, a of n does whatever b of n does. Either they both converge or they both diverge. All right, so we got this guy next. Okay. So, is there a typo in that guy? I think there's a typo in that guy. Nope. Okay. So, what can we do? Well, we know that this is true from many previous sections. So we'll compare it to, since that's our x, that's going to be, so we're going to compare this guy to this guy, which gives us 1. So that's our b of n, which is a divergent series. Since we got a number, they both must do the same thing. So this guy also diverges. Okay, so alternating series. I feel like anyway, so alternating series test, the series this, so they alternate in sign, converges if all 3 of the following conditions are satisfied. Each term is positive, so you're ignoring the signs in front of them. Each term is greater and equal to the following term, which means they get smaller as you go, and the limit of the terms reaches 0. Alternating series bound theorem satisfies the condition of alternating series test, and the truncation error of the nth partial sum is less than un plus 1 has the same sign as the first unused term. So prove the alternating harmonic series convergent, but not absolutely convergent, finding bound for the truncation error after 99 terms. Oh dear. Okay. So they're alternating because it tells us it's an alternating series. Each term is less than the one before because it goes 1, then 1/2, then 1/3, so on and so forth. So it satisfies, so here. So the terms would be, so it would look like this. So those are our terms. So each individual term is positive, ignoring the alternating sign part. Each term is smaller than the one preceding it. 1/2 is less than 1, 1/3 is less than 1/2, 1/4 is less than 1/3, so on and so forth. And the limit of these terms will reach 0 because these terms are essentially 1 over n, which will be 0. So it is convergent. But the alternating series test, this converges. So we did that. Find a bound for the truncation error after 99 terms. So is less than, so u99 plus 1 would be u100, which would be 1 over 100. So the error will be, there we go. After 99 terms, so you have to go to the 100th term. So that's why it's u100, the next term after it. So that's the bound theorem here. And the partial sum is less than un plus 1. Okie dokie. Absolute conditional convergence. So if a series is convergent but not absolutely convergent, we say it's conditionally convergent or converges conditionally. Rearrangements, if A of n converges absolutely in B1, B2, B3, Bn, or any rearrangement, then Bn converges absolutely, and they're equal to each other. So you can just rearrange the terms as much as you want. You still actually have the same thing. Rearrange of conditionally convergent series. If An converges conditionally, then the terms can be rearranged to form a divergent series. The terms can also be rearranged to form a series that converges to any reassigned sum, so we can make anything we want. Okay, show how to rearrange the terms of this to form a divergent series or a series that converges to pi. So let's see here. Okay, so our positive terms, real quick, are going to be 1, 1/3, 1/5, 1/7, 1/9, so on and so forth. Our negative terms are going to be -1/2, 1/4, 1/6, 1/8, 1/10, so on and so forth. So you just figure that out by plugging in. If n is 0, or if n is 1, sorry, this becomes 1/1, so there's 1. When n is 2, you get -1/2 because this becomes -1 cubed, which is -1. Okay, so to form a divergent series, so what you can do is you can just, whoops. So over here you can group enough positive and negative terms. To keep the partial sum from converging. So essentially, we'll add up a whole bunch of these until we get some positive number, and then we'll add up even more negatives until we get negative, and then put some more positive, then put some more negative in, put some more positive, put some more negative in. Bounce it back and forth forever and ever. So here, we would add until greater than pi, and then subtract to less than pi, add until greater than pi, and you repeat, always closing in on pi. So we'll start by overshooting pi, then we'll add some negatives until we drop below it, and then we'll add some positives until we come back above it, but not as far above as this one, the original one was. So essentially, if you think about pi being here, we're going to add terms until we go above, then we'll put some negatives on there until we come below, positives till we come up, but we don't go up as far. So as long as we keep repeating this pattern, it'll converge to pi. So we never go, once we've gone over, we never go over as much again. So our increases wobbling back and forth, but approaching pi. Okay, intervals of convergence. How to test a power series for convergence. Use the ratio test to find the values for x where the series converges absolutely. Ordinarily, this is open interval. In some instances, the series converges for all values of x. In rare cases, the series converges only at x equals a. If the interval of absolute convergence is finite, test for convergence or divergence at each endpoint. The ratio test fails at these points. Use a comparison test, integral test with the alternating series test. The interval of absolute convergence is this. Conclude the series diverges. It does not even conditionally converge for x blah, 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 because for these values of x, the nth term does not approach 0. So, must be a big example next. Okay, yep. Example 6. For each of the following series, find A, the radius of convergence, B, the interval of convergence, identify the values for x where the series converges absolutely and conditionally. Okay, so let's see here. So ratio test, we take, so this is going to be 2n plus 2, because the n becomes n plus 1, and then that 2 distributes over 2n plus 2. So n becomes n plus 1. And then we multiply by the reciprocal of the original. And this is the limit as n approaches infinity. So this becomes the limit as n approaches infinity. We'll group our terms. So 2n over 2n plus 2 times x to the 2n plus 2 over x to the 2n. So this would become, let's see here, 2n over 2n plus 2. this would just become, from x value, x squared. These two ends would cancel out. So let's see here. So if I do the limit, only lead terms matter, so this limit is essentially just 2 over 2 or 1. So this becomes just the absolute value of x squared. So for it to converge, this has to be less than 1, which means our interval is -1 to +1. So the r value is 1. So there's a radius convergence, interval of convergence. Now check out the endpoints. So at +1 and -1. Let's see here. So at x equals the 1s, we get -1 to the n plus 1 over 2n, because this is an even power, so it's always just to be 1. So let's see here. So this is an alternating series. This one, yeah, so this guy will converge as an alternating series test. It meets all the right criteria. So each term is less than the one before. The terms individually are positive, and the limit eventually reaches 0. So for A, the radius of convergence is 1. For B, interval of convergence, so -1 to +1 because it converges at the endpoints. C absolutely was -1 to +1. And D was at the endpoints. Okay. So let's see here. We got this guy. Okay. So limit and approaches infinity. So ratio test. So we take 10x to the n plus 1 over n plus 1 factorial, then flip the original. So this is the same thing as the limit as n approaches infinity. I'm going to do this quickly. 1 over n plus 1. These will reduce. These guys will reduce to just 10x. So this becomes 1 over infinity, which is 0. So this value is 0. So since it's 0, it converges absolutely for all x. So there's no endpoints to check. So since we get 0 here, so r is equal to infinity, or sorry, a, the interval of convergence is going to be -infinity to +infinity, also -infinity to +infinity, so you don't need to worry about the endpoints, and d, none. There are no values where it is everywhere. All right, so let's look at this guy. So ratio test, limit n approaches infinity, n plus 1 factorial times x plus 1 to the nth, all over original. Notice I didn't have to do the flip because my original guy isn't a fraction. Oops, that should be plus 1. Okay, so this is going to become the limit as n approaches infinity of n plus 1. So that's what this reduces to. This is going to reduce to just the absolute value of x plus 1. So this becomes infinity times the absolute value of x plus 1. I needed this to be less than 1. The only way that works is if this is 0. So x must equal exactly -1. So since it must be equal to an exact value, r is 0. There is no radius. So for B, only at the value -1. For C, only at the value -1. And D, none. Alrighty, last one here. All right. Ratio test. So let's see here. Absolute value of x minus 3 to the n plus 1 over 2n plus 2. times 2n over the absolute value of x minus 3 to the nth. So this would become, let's see here, so we've got 2n over 2n plus 2, that's those terms, times the absolute value of x minus 3. So, let's see here, whoops. What do we got here? So this is going to just become 1. So I have, for it to converge, this must be true. So, which would become, so -1 less than x minus 3 less than 1. So that would become 2 less than x less than 4. If I add the 3. Okay. So at x equals 2, if you plug 2 into my original equation, it becomes -1 to the nth over 2 to the n, which would converge. So at x equals 2, we get -1 to the nth, which is a convergent series. It's an alternating series. At x equals 4, we get 1 to the nth over 2n, which is not alternating, so it diverges because that doesn't satisfy the alternating series test. So the radius is 1, it's this number here. B would be from 2 to 4. No, sorry, it converges at 2, so I can put a bracket there. C would be, this would be 2 to 4. And D at x equals 2. Oh boy. All right, here we've got a kind of a summary of the tests. So the nth term test just says, is the limit 0? If it's not, diverges. If yes or maybe, do some more. Is it a geometric series where each term is a multiplier of the previous? If yes, converges to this, diverges to this. If it's not a geometric, try the p-series test, have the form this. It'll converge if p is more than 1, diverge if p less than or equal to 1, and then so on and so forth. Now, so here you've got non-negative terms, so does the absolute value converge, so on and so forth. So integral, ratio, nth root. Ratio test is the one that I prefer just because it gives us very, very simple answers. We don't have to try to come up with another one to check it against. So the ratio test is very, very useful. But that brings us to the end of the section.